Hey guys, hello everyone and welcome to the channel. So this particular video is going to be about Carnot cycle. Now we have already done like many topics from this chemical thermodynamics. This is also one of the most important topic from where CSIR has like continuously asked questions. So I'll be trying to explain this particular topic over here in this particular video. I'll try to go in little detail about it. So I'll be talking more about the concept basically, that what Carnot cycle is. I'll be explaining it in detail, and also we'll be talking about the graph, okay? Because this particular part is very important to understand the graph and how the graph is made. There are basically two types of graphs. One is your PV graph, which we will discuss, and one is your TS graph. So we'll be discussing both of them in the video, okay? So what is Carnot cycle basically? So as the name suggests, first of all, that it's a cycle, right? The name suggests that it's a cyclic process. So it's a cyclic process, that is quite sure. It means what? That the initial state and the final state will be equal, okay? So initial and final states will be same. That's what you can say from the cyclic process. Now there are certain more points about your Carnot cycle. Second is that it's a reversible process, okay? It's a reversible process, and remember, it's a ideal process which we take. So we'll be considering ideal gases in this. So whatever equation we'll be putting equation of ideal gases, okay? So reversible process for ideal gas. The next thing is that we need to find out in the Carnot cycle we actually calculate the work done. Why we calculate the work done? Basically, see what happens, that you have certain source over here, okay? Certain source is there. Source means from where you are getting the heat, okay? So you have source and you are giving that heat to a other object, or we call it as sink. So heat is taken from the source, heat is given to the sink, and this actually is performed by the engine, okay? So our engine perform this, or the heat engine performs this. Now during the taking of heat and giving it to the sink, during this particular process, how much work this engine is doing, that's what is very important to know. Because if you're trying to make a particular engine, or if you're trying to make a particular heat engine basically, using the thermodynamics calculation and all, so you should be able to calculate that how much work you are going to get if you are giving certain amount of heat to the system, okay? So that means what? That it's very important to know that how much work you will get when you are going to give certain amount of heat. So that's what your Carnot cycle is going to help you, your Carnot engine is going to help you to identify. So basically what Carnot engine is actually, so if you are digging upon it, you will find out that in the Carnot cycle there are four steps, okay? There will be four steps. Out of these four steps, two steps will be, like, two steps are going to be isothermal, okay? They are going to be isothermal and like isothermal, that means what? Isothermal process means the temperature remains constant, okay? Or delta T is equals to 0, that means change in temperature will be 0 for that process. And two steps are going to be adiabatic. Adiabatic means where there will be no heat given to the system, neither heat will be taken from the system. So delta Q will be equal to 0. So now I'll try to explain you based upon the graph, okay? So I'll try to explain you on the graph, and then we'll try to understand that how isothermal and how adiabatic processes will be having over here. Alright, so we'll try to understand the complete Carnot process, okay, using a particular system, okay? So the system under consideration is given over here. So currently I have a system in which I have my ideal gas, okay? So I have ideal gas inside the particular vessel over here, and the pressure, initial pressure is P1, volume is V1, and the temperature, initial temperature is T1 for the particular system. All right. Now one more thing which I am going to consider along with this particular system is that I'll be giving a heat source, okay? I'll be considering a heat source also, which I'll show you in the further slides, and also I'll be considering a stand, okay, an insulated stand on which I'll be like, then stand will be in such a way so that the exchange of heat will not be possible over there, okay? So these are the three things, three initial important things of our system. So currently my ideal gas is in the pressure P1, volume V1, and temperature T1, and this is how it is, right? Now what I'm going to do is I'm going to provide a certain heat to this. Okay, so I'm going to do the first process, which is called as isothermal expansion. Okay, so when I will do the isothermal expansion of the gas, so what is going to happen is I have to apply a particular heat source, which is shown over here. So this is my heat source, and there will be a flow of heat. Let's say QH amount of heat is being given to the system. Okay, now if I apply a particular amount of heat, so it's going to change the pressure and it's going to change the volume, but the temperature will remain constant because the process right now is isothermal process. Okay, so right now the first process which I have done is isothermal process. I have given certain amount of heat to the system, pressure and volume has been changed, and the temperature remains constant in this. Now if I have to explain this on the graph, so how I will understand based upon the graph. Okay, so if I have this PV graph, let's say, okay, this is volume on the x-axis and I have pressure on the y-axis. So if let's say the previous position was position A, where my pressure was P1, volume was V1 and temperature was T1. Now if I am changing the system in such a way that the temperature remains constant, so what and how I have to do? So basically I am doing expansion, right? Expansion means the volume has to increase. The volume should increase from a particular V1, the volume will change to V2. So basically for the expansion, it's very common that your V2 will be greater than V1. And in the isothermal process, you know that the gas or the ideal gas follows Boyle's law. Okay, so according to the Boyle's law, what is going to happen, that PV is going to be constant, or you can say that P is going to be inversely proportional to V. So if the volume is increasing, so the pressure is going to decrease. So that means what, if this is said to be the position number B for the system, so from A to B if I move, so I'll reach up to a point B over here, where my pressure is going to be P2, volume is going to be V2, but the temperature will remain same. Understood? So this particular process of isothermal expansion is done in such a way that my pressure is changing from P1, V1 and T1, sorry, pressure is changing from P1 to P2, volume is changing from V1 to V2, temperature is remaining constant. So that's why this process is actually isothermal and expansion process. Okay, now this particular process is also called as your power step. Okay, because what I am doing is I am giving system certain amount of heat, right? So this is going to be called as the power step. Now what will be the work done in this particular step? So using the using the work done formula for the isothermal processes, which we have already discussed in our previous videos, we can directly find out the work done in the isothermal process. Now since the work is done on the system in this particular process, so we can say, because we are doing work, we are applying heat or we are providing the heat to the system. So the work done by the system in this process, WAB is what I will write down. So the work done will be positive over here because we are doing work on the system, and it is going to be nRT1, okay, because we are doing it at a constant temperature T1. R will be your gas constant, N is, let's say, the number of moles of the gas which are over here in this system, okay, and it will be ln V2 by V1. Okay, so this is going to be the work done during this particular process, which is your isothermal expansion. Okay, so that's the first and the important step of your Carnot cycle. You have expanded your gas from point A to point B. The pressure decreased because of the Boyle's law, volume increased because of the expansion, temperature remained constant because it's isothermal expansion, and that's what your work done is going to be. Now let's go upon the other process. Now once the expansion has been done isothermally, what I'm going to do is I'm going to stop giving heat to the system. Okay, I'll stop giving heat to the system, and that's how I'll create the other step of it. So in the next step, which is called as your adiabatic expansion, so what is going to happen over here, that the process over here is such that the heat which was earlier given to you in the second step, that means during the isothermal expansion, the heat which was given to the particular system, that particular heat only is sufficient for expanding it further. Okay, so what I have done, I have taken up my system and I have kept it on the insulated stand. Okay, on the insulated stand, so that there is no change of heat. Okay, so delta Q over here is 0. That means I'm not giving heat to the system, neither I'm allowing heat to come out of the system. So whatever heat is there in the system, the internal energy of the system is going to be responsible for the expansion now. Okay, so that's why this process is called as adiabatic expansion. Now when you do this particular thing, your temperature will come down. Okay, so during adiabatic expansion, since the internal energies, whatever the energy was contained in the system in the previous step, that only heat is being utilized for the further expansion. So obviously your temperature is going to change. So the new pressure is going to be P3, the volume is going to be V3, and the temperature is going to be T2. Now remember this thing, that your T2 is actually smaller than T1. Okay, so T2 will be smaller than T1, and since it's expansion, so obviously your V3 is going to be more than your V2. Okay, and the pressure is going to be decreased. Okay, so the pressure will decrease, volume will increase, and the temperature is going to decrease. So if I show this in the graph, so this is how it is going to look like. So if I draw this in the PV curve, so this is my P, this is my V. Earlier I did it from point A and I moved it till point B, let's say. Okay, here I was having P1, V1, T1. Here I was having P2, V2 and T1. Now in this particular process, which is step B to C, I'll be reaching to this point C, and here my pressure is going to be P3, volume is going to be V3 because volume will increase, you can see from here, and the temperature is going to be T2. So that's how this particular process will be, and this will be called as adiabatic expansion. Okay, so that's your adiabatic expansion. Now if you have to calculate the work done during this particular process, so that also we can easily do. Now the work done during this particular process, that is called as WBC, can be calculated. Now since this particular process is an adiabatic process, so this will be given by NCV. CV will be your heat capacity at constant volume, and this because it's an adiabatic process, right? So NCV, and it will be equal to T1, sorry, T2 minus T1. Okay, so that's what your work done during the BC processes. So final temperature minus initial temperature. So that's going to be the work done during this particular process. And remember, there is no transfer of heat in this process. Okay, so no heat is given to the process. So again, just to summarize this adiabatic expansion, what we have done, we have expanded it from pressure P2 to P3, volume has changed from V2 to V3, and your temperature changed from your T1 to T2. The temperature will decrease, pressure will also decrease, but the volume will increase because it's a expansion process. So you can see from here. Okay, that is the expansion process, and that's how it is going to increase. Now we are now set up for the third step, which is going to be the compression. Okay, so the next step is called as your isothermal compression. So in the isothermal compression, what we are going to do, we are going to compress the system in such a way that heat will be given from the system to a sink. Now sink is a sink is a particular you can say it's a reservoir which is at lower temperature, so that heat can flow from system towards the sink. Okay, so now you are actually allowing heat to flow from the system to outside, and you are changing the pressure and volume over here. So this is called as your isothermal compression. Now in this particular thing, in this particular step, what you can see that let's say this is QC is the amount of heat which is given to the sink. Okay, QC means the heat for the colder substance, and P4 is the pressure, V is going to be the volume, V4 is going to be the volume. Now since it's a compression, now obviously your V4 will be smaller than V3. Okay, so whatever volume was there for the previous step, it is now decreased here, and the temperature is constant because the process is isothermal process. Now again, you can show this in the PV curve. So if you want to show all this thing in the PV curve, you will get to see in such a way that earlier you were having from A to B, you went from point A to point B, the pressure was P1, V1 and T1, and here it was P2, V2 and T1, and then you went from B to point C, let's say, where pressure was P3, volume V3 and the temperature was T2. Now you are compressing, so you are actually going in the reverse direction like this. Okay, and you are reaching to a particular point D, and here the pressure is going to be P4, volume is going to be V4. So see, pressure is going to increase because you know it's isothermal process, and it is going to follow the Boyle's law. So if you are decreasing the volume, your pressure is going to increase. So that's why your P4 will be greater than your P3. Okay, so that's why it is little higher in the curve than P3. Temperature remains constant here. So this process is your isothermal compression. Okay, so this is isothermal compression which you are going to get. Now what you can see or what you can find out is the work done during this particular process. So the work done during this particular process, WCD, can be written in this form, that is equals to your minus nRT, and that should be T2, and it will be ln, and it will be V4 upon V3, because minus sign, because now work is done like on the system. Okay, so that's why we are going to put a negative sign over here, and that's how this is going to be. Okay, so yeah, so that's what your work is being done in this particular process during C2D. Similarly, we can go to the last process, which is now going to be the last process, which is going to be the adiabatic compression. So talking about the last process, which is your adiabatic compression, here you can see that what I have done, I have again kept the system on the insulated stand over here, and I am allowing it to compress more, such that my pressure, volume and temperature reaches the initial condition. Then only the complete process is going to be a cyclic process, and in order to make sure that I am doing it adiabatically, that means the heat given to the system over here in this process is actually 0. So if you look upon the complete in the PV curve, so basically this is how I am going to get. So we have started our process from point A, where it was P1, V1 and T1, and then we have expanded isothermally to point B, where it was P2, V2 and temperature was T1 itself. Then we have expanded adiabatically to point C, where pressure was P3, volume was V3 and the temperature became T2. And then we just compressed it isothermally to point, let's say point D, where my pressure was P4, volume was V4, temperature remained T2. And in the last step, where my which I am doing over here is this, where I am doing it like called as adiabatic compression. Okay, so this is what we are doing, adiabatic compression. So by far we have completed our cycle. And if I show you all the processes over here, so the first process AB was your isothermal expansion. Okay, isothermal expansion. Your BC was adiabatic expansion, and your CD was your isothermal compression. Okay, and then your DA is your adiabatic compression. So that's how the two pair of isothermal expansions, two pair of adiabatic expansions, that's what we got. Now the work done during this particular process can also be calculated very easily. So the work done during this process will be given by WDA, and that is going to be equal to NCV, and it is going to be T1 minus T2. Okay, so that is going to be my total work done. Now for the complete cycle, if you want, so for the full cycle, if we have to calculate the work done, so how we are going to do that? So for the complete cycle, W total, that is total work done, will be given by WAB plus WBC plus WCD plus WDA. If I put all the values, so what I am going to get is something like this. That was the first process was nRT 1, and it was ln V2 by V1, plus the other process BC process, we were having work done of CV, and it was like T1 minus T2. Okay, and then we will be having plus, and it will be like minus nRT2 and ln V4 by V3. Okay, that's what we got. And then we were having plus CV, and it was T2 minus T1. So you can see that these two processes, this particular one, like the process CV T1 minus T2 and CV T2 minus T1 can be cancelled out. because this is just reverse of that, right? So if you put negative sign over here, you can write down T1 minus T2, and these two can be easily cancelled out. So basically the work done will be actually the sum of these two. So we are just left out with these two terms over here. Now using the ideal gas conditions, we can say that T1 V2 to the power gamma minus 1 is actually equal to T2 V3 to the power gamma minus 1. We are just taking the adiabatic conditions, okay? And similarly, we'll be having T1 V1 to the power gamma minus 1 will be equal to T2 V4 to the power uh, gamma minus 1. Okay, so that's what we are going to get. Now if you just compare all of them, what you will get is V2 by V1, that is going to be equal to V4 by V3. Okay, so in the place of V4 by V3, I can simply put V2 by V1. So taking that into the consideration, my W total, that is total work done, will be equal to nRT1 ln V2 by V1, and this will be equal to minus nRT2, and this is going to be ln and V2 by V1. Okay, so that's how I can just put them, and I will get the work done over here. Now the overall work done, since these terms are going to be common for both of them, so the total work done can be easily written as nR T2 sorry nR T1 minus T2, and it will be ln V2 by V1. So this is going to be my total work done. Okay, so the total work done for the Carnot cycle can be easily calculated by this particular step, and that's how we have derived the work done formula for the Carnot cycle. So that is going to be the expression for calculating total work done for your Carnot cycle. Okay, now this is one part of your derivation, and that's one part of the equation which you need to memorize. Now let's try to understand the whole system on the basis of our TS diagram. Okay, now just consider that instead of expressing everything in the form of PV diagram, I am expressing in the form of TS, T for temperature and S for entropy. So I'm expressing in that particular process. So when I was at point A, remember point A to B, that was isothermal process. That means there was no change in temperature. So that curve is going to be a straight line. Okay, so point A to B is going to be your isothermal process, and there it's going to be a straight line in the TS curve. Now the next process, which was from B to C, remember that was your adiabatic process, and the change in entropy for the adiabatic process is 0. So that means the entropy is going to be constant for the next process, that is for process from B to C. So this is going to be your adiabatic process. Okay, so this is adiabatic process. So when you are going from point C to D, that's again going to be isothermal process, and the change in temperature again is going to be constant. So this is isothermal process, and this is going to be your point D. And at the end, when you are going from D to A, that's again going to be your adiabatic process, and the change in entropy is going to be 0. So that's how your cycle is going to be made in the TS diagram. This is adiabatic. So that means what? That in the TS diagram you will find out a rectangle. Okay, that's going to be a rectangle. Now one more thing which I wanted to express you, which I just wanted to explain you in the work done when we have calculated. So with the help of diagram also, with the help of graph also, we can calculate the work done. Work done is actually equal to the area under the curve. Okay, so if you want to calculate the work done by AB process, you just have to find out the area under the whole curve. So total work done will be equal to the work done under the AB curve. Okay, that is going to be the work done during the AB process. Okay, so this is going to be the work done during your AB process. So this complete is going to be the work done during your AB process. And when we have to calculate the work done under BC process will be 0, and the work done between CD process or during the process CD is going to be given by this particular shaded region. Okay, so this is going to be the shaded region for the work done in the CD process. So if I have to calculate the total work done, that should be equal to the difference of work done during AB process minus the difference of work done in your CD process. Okay, because one process the work is done by the system, in the other process work is done on the system. So we have to take difference of them. So that's why the rectangle in the center which you are getting is actually going to give me the total work done. Okay, so W total is going to be the area under this particular rectangle. In the same way, if you are considering the the PV curve, so there also the area or the total work done will be actually equal to the area under this particular curve. So this area is going to give you the work done, the total work done of the system. Alright. Let's try to understand the complete process and how the graph changes the PV curve and the TS curve side by side during the particular process. So you can see right now on your screen through that animation I have just tried to explain you that how the graph changes during the change in the processes during the complete Carnot cycle. Now as we have understood the work done, let's try to just finish this topic by understanding the efficiency of the system. So the efficiency of a Carnot cycle is, or the Carnot engine is denoted by a letter eta, and it's actually equal to, the eta is actually equal to the ratio of energy output, okay, how much energy you are getting out of the system divided by the energy input, okay, so how much energy you have given to the system. So this has been expressed, or this can be expressed in two forms. One is based upon the temperature. So if you are expressing in the terms of temperature, so your efficiency will be equal to T, we were having T2, right? So sorry, we were having a high temperature that was T1, and minus we were having a low temperature that was T2, and divided by T1. Okay, so that is going to be your efficiency. For the sake of understanding, you can write down in this way, that is eta is equals to T high, okay, that means high temperature, minus T low, that means low temperature, and divided by T high. So that is going to tell you about the efficiency of the Carnot engine. So this is in the terms of your temperature. You can also express this in the terms of your heat to the system, and also in the terms of your work done. So in the terms of your work and heat, you can write down that eta, that is efficiency, is equals to total work done divided by the heat which was taken by the system, the input, that was what we did in the power step. So heat given to the system was QH, right? So the work done, it's actually the difference of both the heats which you have given to the system minus the heat which was taken out of the system, that was given by QC. So the difference of both of them and divided by QH. So basically this is the equation where you will get efficiency in the terms of your heat given to the system. So overall your efficiency you can write down in the terms of both the temperature and your heat. So let me just summarize everything. So in order to summarize, I can write down that my efficiency is actually equal to 1 minus QC divided by QH. I can just I can just divide them separately. So that's what I would get in the terms of heat to the system, and in the terms of temperature I will get 1 minus, and I will get T2 by T1. Okay, so that's going to be the formula for efficiency. So that's all for this particular video, guys. We have discussed about the Carnot cycle. We have discussed all the processes. We have calculated the total work done. We have calculated the efficiency of the system. Also, we have understood both the graphs, that is PV graph and the TS graph. So I hope this video was a helpful video. You guys understood it well, and you guys got to know a few new things. And if you want me to continue this particular series, do let me know in the comment sections below. And if you like this video, give it a like. Thank you so much for watching this video, and I'll see you guys in the next one. And till then, have a great day. Take care of yourself, and bye bye.